Hi, in this video I want to show you how you can take these three physics equations and combine them in a way to produce a new equation so that we can more easily measure motion. Kinematics is the branch of physics where we try to measure the motion of an object without trying to explain why it happens or how it happens. And there's a way to rearrange these foundational equations to come up with new tools, new equations that are just quicker and easier to use so that we can keep track of an object's motion. So I want to show you how to do that here today by focusing on first these two equations and pointing out that they both are an equation for the average velocity of an object. However, when I set these two equations together, I can, instead of saying that the average velocities are equal to each other, it's also true that this other half of the equation, these are equal to each other as well. So what I mean is, we can say delta x over t is equal to the initial velocity of an object plus its final velocity all over 2. And by putting these two together, I've eliminated the average velocity term, and now I just have this algebraic equation. With my next step, I'd like to multiply both sides of this equation by acceleration. Okay, so when I do that, this marker is still not working. Let's try this one. Okay. Multiply by acceleration on both sides, but I want to take advantage of this equation, specifically the fact that acceleration is equal to the final velocity minus initial velocity over time. I want to take this part of the equation and substitute it here. So now I'm multiplying on the right side of the equation by the right side of this equation. It's still true that the left side is equal to this side on the right. It's just here it's acceleration and here it's acceleration but written in a different way. So I'm still doing the same thing to both sides of the equation, so I'm not violating any mathematical laws here. All right, when doing that, I can simplify a little bit here. So let me rewrite this now after multiplying. So acceleration times the displacement over time over here. And then simplifying this one, we're going to multiply the numerators together and the denominators together. We're going to have to do kind of a FOIL method over here. So that'll be VI plus VF times VF minus VI. And then we multiply the denominators together, so that's just 2t. Now, when I'm going to take a shortcut here. I'm going to multiply both sides by 2t to get rid of this denominator. I want to get rid of the fraction over here. So I'm going to multiply this side by 2t as well. Notice 2t's, they are canceled out here. And then notice that the time is also canceled out over here. Not the 2, but the time. So rewriting this one more time, we have 2 now times the acceleration times the displacement. And then I'm going to go ahead and multiply these two quantities together. So when I do that, I use the FOIL method. I'm going to end up having the final velocity squared minus the initial velocity squared. Okay, so there's a lot of subscripts and symbols to keep track of here. So this is the final velocity squared. Okay, initial velocity squared. And I'm going to do one last thing. I'm going to add the initial velocity to both sides, just for some convenience, because we're often looking for the final velocity of an accelerating object. So by doing that, these are gone, and the final velocity, I'll move it to the left side of the equation. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. So this equation, oh, I'm sorry, can't see that. This equation is a new kinematics equation that is really useful because if you notice, it doesn't have time in it at all. So if you're limited on information and you don't know how long an object has been moving or accelerating for, then you can use this equation instead. Assuming, of course, that you have the displacement of the object and how much acceleration it has and all that. So I'm going to rewrite that up here at the top. So now we have 4 key tools that we can use to measure the motion of an object. So let's try this out with an example problem. So in this example, a fighter jet attempts a landing on an aircraft carrier, and it starts at a velocity of 64 meters per second and slowing down at negative 30.0 meters per second. Will it stop before running off the 100-meter runway? So we have a lot of information about this jet plane here, and we have to be very careful because this could be a very tricky problem unless you're paying attention to what information is actually about the jet and what information is actually about the setting. We're going to focus on the information given about the jet only. Okay, so we know, for example, that the jet started out at 64.0 meters per second for its starting speed. And we know that it's slowing down at a rate of negative 30.0 meters per second. So that is an acceleration. We also are told, we're asked the question, will it stop before running off the 100-meter runway? We don't know if the plane has gone 100 meters or not, so we're not given the displacement here of the plane. We're given the total length of the runway, but that has nothing to do with the plane. So we're going to ignore that piece of information for now. The 100 meters is not relevant to the actual motion of the plane. So just for the motion of the plane, we do know that the plane is going to stop, or at least we're going to try to test it out and see what would happen if we stopped the plane in this example. What will that be for our displacement? So we're going to say that the plane has a final velocity of 0. So at the end here, it's not moving at all. So all that said, now we are ready to write this down in physics language. The initial velocity is a positive 64 meters per second. Our acceleration here is, the plane is slowing down, and so it's a negative 30.0 meters per second squared. It was moving in the positive direction, it slows down, so that acceleration is negative. And then the final velocity of the plane, we're going to say is 0 for the purpose of testing this out to see if it's true or not that it's going to stop in time. So what we really want to know is, does the plane stop before running past the 100-meter displacement? So what would be the displacement of this plane given these constraints here? So we want to know what is the displacement of the plane. Looking at our equations from before, we have 4 options so far to look at, and we want to have an equation that gives us the displacement in some way. So I see 2 equations that have displacement in it. This one has an average speed and a time. We don't have the average speed or time of the plane. We could find the average speed, but we're not really given a time right now. So instead, we're going to use this equation over here. So I'll write that down on this board as well. The equation is the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. Excuse me. So I want to rearrange this equation before substituting. I want to solve for the displacement here. So that's going to take a couple of steps actually. I'm going to subtract VI, or initial velocity, on both sides here of the equation. So that's going to give me the final velocity squared minus the initial velocity squared is equal to 2 times the acceleration times delta x. And then I'm going to divide both sides by 2a. So I'll rewrite our final form of the equation here, solved for the displacement of the plane. So that will be delta x equals the final velocity squared minus the initial velocity squared all over 2 times a. 2 times acceleration. So now that I've got that solved, I can now substitute in my numbers here for the displacement. So I'm going to do that over here. The final velocity squared is just 0 squared minus initial velocity, which is 64 meters per second, all over 2 times the acceleration, which is negative 30. I should include my units here. I like to keep track of my units as well, even though it gets a little messy. So 64 squared is 4,096. And that's got a negative sign in front of it. It's not included in the square. So 4,096 meters squared per seconds squared. So the square gets distributed to the units as well. So meter squared over seconds squared. And that's divided by negative 60 meters per second squared. So we do the math here and we see that the displacement of the plane is 68.3, and then meters squared per second squared divided by meters per second squared. Almost everything cancels out except for one of the meters on the top here. So 68.3 meters is our displacement of the plane. So does the jet stop in time? It takes 68.3 meters of distance for it to stop. So the answer is yes. It stops before it runs off the 100-meter runway. So that's all I've got for you in this video. Remember, everything you have is a gift.